Well, scientists like to classify things. That's one way to make some sense out of overwhelming amounts of information. So we're going to take matter, which is anything you can see, and some things that you can't see, and we're going to group it, break it into categories. One way to do this is by looking at states of matter. States, maybe I should just not point at all. States of matter, solids, liquids, and gases. It's going all by itself. I don't know what its problem is. Liquid water, we're all familiar with. Hopefully you drink that at least occasionally, or you wouldn't be here. We're familiar with solid water. We call it ice. And we are also familiar with water in the gas state. We often refer to that as steam, right? There is water in the gas state in the air that we're breathing. We sometimes call it humidity, okay? And you can feel it when there's more water in the air. All matter can be divided into these three categories, solid, liquid, or gas. And the characteristics of these three groups depend on how the particles of the matter are interacting. In the solid state, the particles of the solid are in close proximity to one another, and they're not moving relative to each other. So if this is molecule A and that's molecule B, they're always going to be next to each other. That's not to say that they aren't moving, though. They're vibrating. Students also come in three states. You guys are currently in the solid state. You're sitting close together, and you're not moving relative to each other. We're not milling about the room. But are you absolutely still? No. You're scratching your ear, you're blinking, thank goodness, you're breathing, right? Fidgeting, maybe somebody is taking notes, that'd be awesome, right? You're moving. All matter, all particles of matter are in motion, but sometimes it's just like you guys right now, just kind of fidgeting in place. In a liquid, the particles are still close together, but now they're moving around relative to each other. So that's like in lab. When we're still pretty close together, it feels kind of tight in that room with 35 students or so in there, but we're moving around the room. That's what water molecules do in the liquid state. In the gas state, there's a great deal of space. This isn't really to scale. There's a great deal of space between the particles, and they're just going off in random directions. That's when class is over and that door opens and you guys are like gas molecules and you go out the door and you go in all kinds of different directions and you're far separated from each other. That's what the particles are doing in these three states of matter. So now that I've said all that, we'll go over these slides which have it all typed out for you. Solid state. The particles are packed close together, fixed locations, fixed relative to each other. They're vibrating, oscillating, fidgeting, but not moving around. Solids have a fixed volume and a rigid shape. If you take a block of ice and you put it in a different container, its shape stays the same, its volume stays the same. That is not true of liquids and gases. We can divide solids into more subcategories. One distinction is crystalline versus amorphous. So a crystalline solid, these form crystals, and the individual particles have a regular, repeating, three-dimensional arrangement. You students would be in the crystalline form right now because you're sitting in rows in chairs. If you imagine a kindergarten class coming and sitting on the floor around the teacher for story time, do they naturally sit in rows? No, they sit all random next to each other, right? Some of them aren't even facing the teacher. That would be amorphous. Crystalline, there is order. Amorphous means without shape. And so the particles are just randomly stuck together. So here's a picture, an illustration of an amorphous solid. In the liquid state, particles are still close to each other, but now they're free to move around. Liquids have a fixed volume because the atoms are still close together. If you take a cup of water and pour it into a big bowl, has the volume of the water changed? No, it's still 1 cup of water, but its shape changed. The particles are free to move around, but they still have to be close to each other, and so the volume of a liquid is constant. But liquids assume the shapes of their containers. In the gas state, there's lots of space between the particles. They're free to move relative to each other, and they basically don't even know that the other molecules or atoms are there. Because there's so much space between them, gases are compressible. If you put a solid or a liquid into, this is a piston, and you press down on it, you can't push that plunger down anymore. There's no extra space that you can squish out. These particles are packed in there as close as they can be. You cannot compress liquids and solids. Gases are compressible. There's lots of empty space. You put pressure on that piston, you push down hard, you can squeeze it together. You can squeeze the gas together because of the empty space. So gases are compressible. Gases always take on the shape and the volume of their container. If you take a small vial of gas and open it in a large room, those gas particles are going to move and keep moving until they take up the whole space. That's why, you could open a jar of something really stinky. Name something stinky. Blue cheese. Blue cheese is stinky. So I've got a little thing of blue cheese over here, and it gives off an odor, right? The odor is in the gas state. If I open that over here, it's not going to be too long until everybody, even in the back row, can smell it, because that gas is going to expand to fill the whole room, right? Think of somebody with, like when my kids eat onions, then they toot, right? Oh my goodness, it fills the whole house. Gases expand to fill their containers. This table just summarizes the ideas that we've talked about. So I'm not going to read that to you. You can look at that yourself. It's in the book also.